Namaskaram. Welcome back to the final lecture of the symmetric group series. Okay, let's start. Let sigma belongs to Sn. Then the first part is sigma is a product of n sigma symbol transposition. And second part, we have to show that n sigma is the minimum such symbol transpositions. For establishing first one, we will use induction on n sigma. So first of all, we assume that n sigma equal to 0. By using this proposition, we know that if n sigma equal to 0, then sigma equal to I. We can identify identity map is the empty product of symbol transposition. So this result is true when n sigma equal to 0. Next, we assume that n sigma is positive. So n sigma is positive means sigma is not equal to I. Okay. Our induction hypothesis is eta is a permutation in Sn. If n of eta is less than n of sigma, then result is true. True means eta is a product of n of eta symbol transposition. That is our assumption. We have to show that sigma has such expression. According to this proposition, we know that there exists an I from this collection such that sigma I is greater than sigma I plus 1. Then by lemma 2.9.3, this implies n of sigma Si equal to n of sigma minus 1. This implies n of sigma Si is less than n of sigma. So by our induction hypothesis, this sigma Si can be written as product of n of sigma minus 1 symbol transpositions. Then it is clear that eta Si can be written as product of n sigma symbol transpositions. And what is eta Si? Eta is equal to sigma Si. So this is equal to sigma Si into Si. Si is a transposition. So we know that Si into Si is identity. So this is equal to sigma. So sigma can be written as product of n sigma symbol transposition. Okay, for the second part, we have to show that n sigma is the smallest such number. Let L of sigma denote the minimum number of symbol transpositions needed in writing sigma as a product of symbol transposition. Then it is clear that n of sigma is greater than or equal to L sigma because L of sigma is the minimum. We have to show that L of sigma equal to n sigma. We have to only show that L of sigma is greater than or equal to n of sigma. Here also we use induction on L of sigma. So the case 1, L of sigma equal to 0. We know that L of sigma equal to 0, then sigma is identity map. Then already we know that n of sigma is also 0. So the result is true for when L of sigma equal to 0. Next we assume that L of sigma is greater than 0. Then what is our induction hypothesis? If L of tau, where tau belongs to Sn, L of tau is less than L of sigma, then L of tau equal to n of tau. We have to show that L of sigma equal to n of sigma. We know that sigma can be written as product of L of sigma symbol transpositions. Let it be S of j1, S of j2, etc. S of j, L of sigma. Next we post multiply both sides by this last transposition. So this become I. Okay, what about the left hand side? Sigma of Sj of L sigma equal to here Sj1 up to Sj L of sigma minus 1. So right side contains only L of sigma minus 1 symbol transpositions. If you denote this transposition as Si, that means we can find a symbol transposition Si such that L of sigma Si equal to L of sigma minus 1. So now L of sigma Si is less than L of sigma. Okay, so by our induction hypothesis, L of tau equal to n of tau. So here L of sigma Si equal to n of sigma Si. Okay, now L of sigma Si equal to n of sigma Si. And what is L of sigma Si? L of sigma Si equal to L of sigma minus 1. And then from this lemma, we have n of sigma Si equal to n of sigma plus or minus 1. So what is L of sigma? L of sigma equal to this quantity plus 1. So in both cases, L of sigma is greater than or equal to n of sigma. Already we have this inequality. So combining these two, we have L of sigma equal to n of sigma. Next we are going to define sign of a permutation. The sign of a permutation is defined as minus 1 raised to n sigma. A permutation with a positive sign is called even and negative sign is called odd. So it is clear that this sign function has only two possible values, 1 and minus 1. It is clear that this is a group. under normal multiplication of numbers. So this proposition says that the sine function from Sn to this group is a homomorphism. So we have to show that sine of sigma tau equal to sine of sigma into sine of tau. Since tau is a product of simple transpositions, it is enough to show that sine of sigma Si equal to sine of sigma into sine of Si. Okay, consider sigma Si. From our lemma 2.9.13, we have n of sigma Si equal to n of sigma plus or minus 1. Therefore, sine of sigma Si equal to minus 1 raised to n of sigma plus or minus 1. That is minus 1 raised to n of sigma into minus 1 raised to plus or minus 1. So this is always minus 1. So this is nothing our sine of sigma. So sine of sigma into minus 1. And what about this minus 1? We can replace this minus 1 by sine of Si, because for every simple transposition its sign is minus 1 raised to 1. So sine of sigma Si equal to sine of sigma into sine of Si. Therefore this sign is a group homomorphism. So what is the kernel of this homomorphism? Kernel of sine function. That is equal to those sigma belongs to Sn such that sine of sigma equal to identity in this group. Here identity is plus 1. And we know that kernel is always a normal subgroup. This subgroup is denoted by An and it is called alternating group. Okay, then by theorem 2.5.1, Sn by its kernel, now kernel is An, is isomorphic to image of Sn under this homomorphism. And in this case, this homomorphism on 2, so this is equal to plus or minus 1. So what is order of this group? Order of this group is equal to 2. And this can be written as order of Sn by order of An, that is equal to 2. So what is order of An? Order of An is equal to order of Sn by 2. And we know that Sn contains n factorial elements. So order of An is equal to n factorial by 2. Next we will see how to find sine of sigma from its disjoint cycle decomposition. Let n greater than or equal to a transposition tau equal to ij belongs to Sn is an odd permutation. That means transposition is always odd. The second result is the sine of an R cycle x1, x2, etc. xr is minus 1 raised to r minus 1. Okay, before moving to the proof, we consider sine of identity map. And we know that sine is a homomorphism. So sine of identity is equal to identity in the right side. The identity in right side is 1. We know that homomorphism maps identity to identity. So sine of identity permutation equal to 1. Then we can replace this identity by eta into eta inverse, where eta is any permutation Sn. So sine of eta into eta inverse equal to 1. Again we know that sine is a homomorphism, so we can split this is like this, sine of eta into sine of eta inverse, that is equal to 1. So the conclusion is the sine of eta and sine of eta inverse are always same. If this is 1, this also 1. If it is minus 1, this also minus 1. Corresponding to this given transposition, we can find a permutation eta belongs to Sn such that eta of 1 equal to I and eta of 2 equal to j. Okay, we know that sine of transposition equal to minus 1. So sine of 1, 2 is equal to minus 1 raised to 1, that is equal to minus 1. And already we know that sine of eta into sine of eta inverse is equal to 1. So we just multiply these two numbers, sine of eta and sine of eta inverse. So their product is 1. So there is no change in left hand side. And sine is a homomorphism. So you can write this is like this. Sine of eta 1 to eta inverse equal to minus 1. And using our lemma 2.9.8, this can be written as eta of cycle eta of 1, eta of 2. Okay, and what is eta of 1? Eta of 1 is equal to I and eta of 2 is equal to j. So this becomes cycle ij. So sine of transposition ij equal to minus 1. Next we have to find the sine of R cycle. Every R cycle x1, x2, xr can be written as product of transpositions like this, x1, x2, x2, x3, etc. xr minus 1, xr. So this R cycle is a product of R minus 1 transpositions. This is our sigma. So what is sine of sigma? Sine of sigma is equal to sine of first transposition into sine of second, etc. sine of last transposition, because sine is a homomorphism. So what about sine of transposition? We know that sine of a transposition is minus 1 because that is odd. So this is minus 1 into minus 1 into minus 1. How many transpositions are there? R minus 1. So this is equal to minus 1 raised to R minus 1. Sine of a R cycle is equal to minus 1 raised to R minus 1.